So, is your cloud infrastructure leaking money? Honestly, it's a pretty serious question to ask yourself. In the modern pay-as-you-go cloud model, inefficient code isn't just an annoying IT headache anymore. It directly equals financial loss. Every single millisecond your application spends waiting around or processing inefficiently, well, you are paying for that computational dead time. And the financial stakes? They have literally never been higher. 60%. That number right there represents the massive expansion in the Integration Platform as a Service, or iPaaS, market over a single year alone. Companies are pouring hundreds of millions of dollars into cloud integrations right now, basically betting the whole shebang on these platforms to synchronize their massive software ecosystems.
Welcome to The Explainer, everyone. Today, we're taking a deep dive into the performance of enterprise application integration platforms. We're going to examine the runtime systems behind them, analyzing a comprehensive survey that reveals the true cost of slow code in the cloud environment. I am absolutely thrilled to be your guide through this fascinating material. Okay, let's dive into this. Here is our roadmap for today. First up, the cost of slow code. Then, we'll meet our integration platforms. From there, we hit the performance evaluation framework, Dimension 1 on message processing, Dimension 2 on fairness execution, and finally, future runtime innovations. Section 1, the cost of slow code. It is absolutely crucial for us to connect the dots between the software that orchestrates a company's data and the actual financial bottom line. This brilliantly illustrates what I like to call the wallet connection. You can literally trace the path right from the integration platform, down to the runtime system, and straight over to computational resources and financial costs. The total cost of ownership is intrinsically tied to how well the runtime system executes. Think about it. If your system requires more cores and more memory just to process basic messages, your pay-as-you-go cloud bill is going to skyrocket. Section 2. Meet the integration platforms. In this explainer, we're evaluating 9 state-of-the-art open-source integration platforms. We're talking heavy hitters here, like Mule, Apache Camel, Spring Integration, WSO2, and Guarana. Now, to really grasp how these platforms tick, we need to define their architecture. They rely on what's called a pipes and filters architecture. It's best to think about this like a giant factory assembly line. The pipes are your conveyor belts, the message channels. The filters are the processing stations along that belt. Messages, which are our raw materials, travel down the pipes and get transformed at each filter. The runtime system, well, it acts as the factory manager, assigning computational threads to make sure the belt keeps moving. Section 3, the performance evaluation framework. So how do we actually measure if our factory manager is doing a good job? The researchers built a highly specific measuring stick just for this. They mapped out a 3-step methodology journey. First, properties identification, where they looked at all possible quality attributes. Second, properties grouping, clustering them by the specific problems they solve. And third, properties selection. By doing this, they successfully distilled countless, super complex features down to a focused, 10-property framework designed specifically to evaluate cloud computing performance. And that 10-property framework is divided up into 2 distinct dimensions. First, we have message processing, which measures the raw speed and efficiency of our factory. Second, we have fairness execution, which measures balanced task assignment. Basically, how fairly does the manager distribute the workload to prevent things from bottlenecking? Section 4, Dimension 1, Message Processing. Let's see how these open-source tools actually handle the raw speed and flow of data. Now, what's really interesting about this slide is that stark contrast in multicore design. Look at that first column. The answer is completely 0. Literally none of these platforms currently take advantage of multicore processors. While most of them handle distributed execution across different machines beautifully, their runtime systems are surprisingly blind to the multicore architecture of the very processors they run on. But despite that shared gap, one platform does manage to pull ahead in this dimension. Mule really stands out as a top performer. It uses a virtual runtime system with multiple nodes, allowing for just excellent clustering. Plus, it boasts highly flexible threading profiles. This gives software engineers the ability to configure thread profiles globally, by connector, or even by a specific flow. That robust level of control allows it to process massive volumes of messages incredibly efficiently. But raw speed isn't everything. Section 5, Dimension 2, Fairness Execution. We've got to ask, are these platforms actually fair when assigning tasks to our computational resources? Well, the results here are surprisingly terrible across the board, honestly. Starvation detection? Nope. Task complexity awareness? No way. Almost every single platform relies on a super basic first in, first out, or FIFO thread pool policy. They completely ignore the computational complexity of the tasks they're assigning. That means a huge, resource draining operation is treated exactly the same as a quick, lightweight data check.
And this leads to a massive real-world problem. Starvation happens when a thread cannot fetch tasks because other threads have effectively blocked it from doing so. Think about the sheer danger of starvation in a cloud environment. If a vital, lightweight task gets stuck behind a massive, poorly optimized one, your processing literally grinds to a halt. In a pay-as-you-go ecosystem, a blocked thread means you are paying hard cash for dead time.
There is, however, one lone bright spot when it comes to fairness. WSO2 is the exception here. It utilizes a priority-based scheduling policy instead of that standard FIFO approach. By leveraging internal queues configured for different priorities, WSO2 allows critical tasks to jump the queue, rather than just waiting sequentially behind massive resource hogs.
Clearly, there is a significant amount of room for improvement. Section 6. Future runtime innovations. What do the researchers suggest must happen next to truly optimize these systems for the cloud?
To hit true cloud efficiency, runtime systems have got to resolve these fundamental bottlenecks. We're talking zero multicore programming support, statically created thread pools that just cannot adapt, overly basic FIFO scheduling, no awareness of a task's computational complexity, and a complete lack of starvation detection. These technical gaps are the main roadblocks holding back modern cloud integration. So the crucial point is this. The solution requires a massive evolutionary leap. Runtime systems must begin exploiting massive parallel computing and graphics processing units. Furthermore, they need to implement dynamic thread pool creation, using predictive models to automatically scale the number of threads at runtime based on actual, changing workloads. That is how you will vastly reduce cloud overhead. Which brings us to a final, provocative thought for you to walk away with today. As we rapidly move into an era of massive parallel computing, is your runtime system actually keeping up? I highly encourage you to take a hard look at the integration platform in your own stack. Because if it's statically configured, if it's relying on basic FIFO queues and totally ignoring multi-core capabilities, your code isn't just slow, it's actively leaking money. Thanks so much for joining me on this explainer today, and keep learning.